This video is sponsored by PCBWay. Hello there and welcome back to another video. In today's video, I'm going to be solving an issue that honestly, I'm surprised there isn't a great solution for just yet. DIY NAS builds are incredibly popular, and for good reason. Heck, I literally did one just a few videos ago, and the NAS that I use to store all of the files for this YouTube channel is also a custom-built NAS. There is one issue with all of these custom NAS builds though, and I've personally run into it multiple times, and that is that it can be hard to get a power supply that has enough SATA power on it for a ton of hard drives. Now, yes, there are SATA power splitters, but let's just say that a lot of those have a pretty bad rep in the computer world, so I completely understand that a lot of people might not want to deal with those. And yes, you can also get power supplies that just have a ton of built-in SATA power connectors on them, but generally, you have to pretty seriously overspec your unit to do that. Like in my personal NAS build, where I ended up having to pay $130 for a 750 watt 80 plus platinum power supply because it was the cheapest one that had enough SATA power for me. And yes, it's a great power supply, but dang was that expensive, and it's really overkill. So my goal today is to create a device that can add a whole lot of SATA power capability to a system by utilizing a power source that most power supplies, even the cheaper, lower wattage ones like a 500 watt unit, have available. Plus, this source doesn't usually get used in NAS builds because of the hardware in them, and this is the PCI Express power connectors. Basically, any modern PC power supply, even things as low as the 400 or 450 watt units, have at least one of these available on them, and most NAS builds don't utilize it unless you have a GPU installed for the sake of transcoding media for Plex or something. Even then, you probably have a spare available. So why not convert this to a bunch of SATA power? An 8-pin PCI Express cable can handle 150 watts. That's easily at least 9 or 10 drives. Well, there is one major issue with this, and this issue is the reason that you can't find any PCI Express to 8 SATA power cables on Amazon or eBay. The problem is that PCIe power is 12 volts only, but SATA runs on 12 volts and 5 volts. And yes, there was also 3.3 volts at one point, however that has long been deprecated as part of the SATA power standard, and therefore will be mostly ignored in this video. So we need to take a bunch of 12 volt power and pass a bunch of it through as 12 volt power while also converting a large amount of it to 5 volt power. And this is where the first bit of research for this project began. How do I do this? There are a lot of ways to turn 12 volts into 5 volts. You could use a linear voltage regulator, one of the many kinds of DC to DC converters, or technically even a basic old resistor. Now, obviously for this case, a resistor doesn't work because it's super inefficient and our load is dynamic, meaning that its current demands change consistently. Therefore, a set value resistor will not succeed at providing a stable 5 volt rail with several amps of current capacity efficiently. As for a linear voltage regulator, efficiency is the main issue here, combined with the fact that you're not going to find a linear voltage regulator that can provide enough power for this application. They all tend to max out around 1.5 amps, and we're going to need probably around 8 or 9 amps. So that leaves us with the DC to DC converter. And those of you who are familiar with hobby electronics are probably screaming, use one of those LM2596S buck converters, because those are perfect for this application and they're super cheap. And while I can totally see where that suggestion comes from, I won't be doing that. Nor will I be using any other standard hobbyist DC to DC converter, and here's why. Now, do note that what I'm about to say here is specifically applicable to the LM2596 modules, but it also mostly carries over to about 90% of the other buck converters you'll find on Amazon. So it's not just limited to this one case. Alright, so what's the issue with a buck converter like this? Well, the problem is that while it's able to provide power to a simple hobbyist grade project, it's really not cut out to power sensitive hard drives in an always-on data storage environment reliably enough for me to be comfortable with it. Here's what I mean. These modules are not powerful enough for this application. After doing some initial testing, it seems that a hard drive can easily draw around 300 milliamps on the 5-volt rail while active, though most drives quote their 5-volt current draw much higher than that, and I'd like to be able to provide their full quoted power draw without any caveats in this build. One of these modules is only good for about 2 to 3 amps, and with drives that say they want almost an amp at 5 volts, that means I can get 3 drives out of one of these modules. So to power, say, 12 drives, I'll need 4 separate modules, which will take up a lot of space. Plus, it's more modules that can fail or accidentally end up with their output voltage set too high, and it would really suck if you accidentally fried 3 brand new 20 terabyte hard drives by accidentally forgetting to set the output voltage on one of these modules. But there's gotta be more than that, right? Because I could totally use a larger buck converter to get past the current limit issue, and it wouldn't be that hard to build in an overvoltage protection circuit on the 5-volt rail. Well, the issues with these modules don't stop there. They continue with the fact that these modules are cheap. Now, what's wrong with cheap? Well, the question is, why are they cheap? And the answer is that they're cheap because they don't use official Texas Instruments 2596 chips. Nearly every single module you will find uses fakes. The telltale signs on the chips themselves are there, such as bad markings, but also a real 2596 chip costs $6, nearly 6 times the price of one of these modules. Even if you buy 2,500 of the chips at once to take advantage of bulk pricing, it's still $3.46 a chip. This means that these modules cannot be trusted to live up to the specs quoted in the TI datasheet, and most of the time they don't, because they spit out pretty darn noisy power a lot of the time. And on the topic of noise, these modules are proven to well exceed EMI emissions standards, which in the case of a computer, especially one with lots of drives and high-speed data transfer happening, could increase the likelihood of things like bit flips and data corruption, and could possibly even cause full-on dropouts and failed transmissions between the devices installed in the computer. Alright, and with that, I'll stop. But I wanted to cover my butt because I know people are going to wonder why on earth I went with as expensive a solution as I did for this problem, and now you know that the reason is because I can't trust the cheap solution. Remember, this is connected to your hard drives that store your data, and if it fries them or craps out on you, because it's the power source, it's probably going to take out enough drives to well surpass the amount of fault tolerance in your RAID array. So you're going to have a very, very sad dataless day if that happened. So what did I choose for this application instead? We've ruled out plenty of stuff, so what's actually suitable? Well, I would like to introduce to you the Meanwell RSDW60F-05 DC to DC converter, or technically this is the smaller 40-watt variant that's also half the size, and this is going to serve as a stand-in for this part of the video because the 60-watt one hadn't arrived yet. Anyway, the RSDW60F-05 is a DC to DC converter from Meanwell, a very reputable power supply manufacturer that can convert an input voltage anywhere between 9 and 36 volts DC to a steady 5-volt output while providing up to 12 amps of continuous current. So that's a pretty darn cool component. It's not cheap at around $45 a piece, but it's from a reputable manufacturer, has a datasheet that both looks very promising and that I can trust the module to actually live up to, passes EMI emissions regulations out of the box without any special PCB design requirements or external components, is powerful enough for my application, and it's really efficient. So it literally checks all of the boxes I need for this application and gets a half point on price because while it's way more expensive than I think everyone would like it to be, its specs justify the price and it's way cheaper than the other options I found, meaning it's also not prohibitively expensive for this project. So let's test out our circuit. I designed a circuit that does the basic thing of creating a 12-volt and 5-volt rail, and I also have a small delay in the drive power-up that gives the DC to DC converter a moment to power up and stabilize before a big load is placed on it. Then, I also built in some other circuitry that allows the drive's power to be staggered with 3 stages to reduce transient current draw from the power supply. Though I recognize this may not be that important a thing for most people, so I also added an option that allows you to easily disable this circuitry. After prototyping this circuit on a breadboard, everything seemed great, but once I started adding more drives, they stopped spinning up successfully, and I found out that this was because the voltage rails were absolutely collapsing after passing through all of my circuitry, and I found this really weird. I checked and made sure that my MOSFETs wouldn't have this issue in their datasheets with the gate drive voltages that they were seeing, and yeah, I know they're all P-channel FETs, but they should be good enough to handle this. They're IRF 9640s. So I troubleshooted for a long while, and as a sanity check at the end, I built up the same circuit, but I replaced all of the P-channel power FETs with relays. This seemed to improve the situation, but it wasn't doing what I needed it to still. This led me to come to the conclusion that the issue was to do with breadboard parasitic resistances, as those tend to be pretty high and can cause issues with higher power prototypes like this. Overall, the circuit's general functionality seems to be nailed down, so I pushed forward with ordering a PCB, though I was still kind of worried about the FETs. So I designed two separate boards, one board that uses P-channel FETs as initially planned, and another board that was designed around some Omron relays as a backup option. Then I headed over to the website of today's video sponsor, PCBWay, and placed an order for both kinds of boards. PCBWay is a company that offers custom manufacturing services, and they have a ton of different capabilities, ranging all the way from PCB manufacturing and assembly to 3D printing with both basic and specialty materials, CNC machining, whether that's turning, 3-axis or 5-axis, and they also offer things like injection molding and sheet metal forming. If you're a maker and want your projects to come to life in a professional way, I can't recommend PCBWay's manufacturing services enough. A custom PCB or CNC machined faceplate can add so much to a project, no matter what it is. And a 3D printed part for a project, when you don't have a 3D printer, can make the project happen in its entirety. I strongly recommend that you check out PCBWay at my referral link in the video description, and now let's get back to the project. A while later, my two different PCB designs arrived, one in red and one in green, but wait, those aren't different. Well, I mean, I exported the files at nearly 3 in the morning, so I probably messed it up and exported the same board under different names and thought it was good, right? Well, actually no, I didn't. The files are right, and it looks like PCBWay might have messed up here. I feel very awkward saying this right after the ad read, but I believe in transparency with sponsors, so it's important I mention this. I reached out to PCBWay through their standard customer support channels so as to avoid favorable treatment considering that they sponsor me, and the issue was quickly resolved. Unfortunately, the timing wasn't on my side, as I reached out basically the day before their whole office went on holiday for Chinese New Year's. But they were kind enough to respond to my dispute within a couple of hours of filing it to inform me that it would take a little while to sort things out because everyone was going to be on holiday. Once they were back in office, the discussion continued, and after only 3 emails over about 2 days, so really quite a short interaction, I had my refund for the mismanufactured boards. In the end, I think this issue was handled extremely well, and I'm really glad to see this. Let's proceed with the FET version of the PCB design, which thankfully is the design that I'm planning on actually using, and the other version was just ordered as a backup in case this one didn't work. And hey, I get to choose between green and red while having both of them in front of me now. Nice. Assembling this board is super easy, as I intentionally only used through-hole components. This is because I know that SMD components, while really not being that bad to solder, can be off-putting to people who may want to build this project themselves, but who have also never soldered SMD parts before. So I stuck to through-hole stuff, and honestly, there's nothing special about assembling this board. Once the PCB was assembled, I tested it out on my bench power supply first, before plugging it into a full ATX power supply that will deliver tens of amps if there's any kind of problem on the board. Thankfully, the PCB powered up beautifully, and the staggering sequence went exactly as I hoped it would. So I moved into plugging the PCB into an ATX power supply, and one cool feature of this board is that even though it's got an 8-pin power connector on it, it's completely agnostic as to whether or not you plug in a 6-pin or 8-pin cable. Both will provide enough power for the board, and it won't take issue with either. Thankfully, nothing changed when I plugged the ATX unit into this board, and it still powered up as expected. Also, when I put a jumper across the pins that bypass the staggered startup sequence, all of the 3 zones of SATA power powered up at the exact same time. Awesome. And so now, it was time to connect the SATA power cables to this board. I bought these SATA power distributors manufactured by StarTech from Amazon, and before you go at me saying how you dare say this solves the issue of using SATA power splitters when you're literally using 4-way splitters to get the power out of this board, let me explain. These cables, minus the input end that connects into a SATA power connector instead of some modular power supply interface, are identical to the SATA cables that would come with a modular power supply and have 4 SATA connectors on them. I'll be cutting off the end that makes these cables into splitters, therefore making them really just regular SATA power distribution cables. But if that still doesn't sit right with you, go ahead and buy some Corsair Type 4 modular SATA power cables and cut off the 6-pin connector that goes into the power supply. Then you can be absolutely sure that your SATA power cables are going to be of good quality. After finding out which one of the 5 wires in these cables was the 3.3 volt wire, I cut it off because, as I mentioned earlier, the 3.3 volt power on SATA power cables has been deprecated for a while, and the drives that will be used with this board shouldn't need it, and I moved on with connecting the 12 volt and 5 volt wires. I had to sort out which wire was 12 volts, which one was 5 volts, and which 2 were the remaining ground cables before I could put them into the 4-pin screw terminals on the board, and frankly, this would have been a lot easier if my cables weren't black, but it was still doable. As a quick side note, I would recommend using ferrules if you have them for these connections, as these terminals aren't the best to be used with straight stranded wire. But either way, no matter what you do, don't tin the wires before putting them in the terminals, as that's a great way to cause a loose connection and a future fire hazard. After getting one cable connected, I stopped and tested the board out before connecting the other 2. With one drive connected, things spun up perfectly, and this was a huge relief to see. However, we're not out of the woods yet with the collapsing voltage rail issue. Before I can call that a non-issue, I've got to test it with some more drives. After plugging a total of 3 drives into the cable, I tested everything again and could tell that all 3 drives were spinning properly. So it seems that our voltages are good, as this wouldn't work on the breadboard. Now I pushed forward with connecting the other 2 cables, and here we are with 3 drives hooked up, 1 to each cable, to make sure that the staggering works properly, and it does. Alright, let's get to the big, final test for this little board. Powering all 8 of the SAS drives in my recent DIY budget NAS build. These drives are pretty power hungry, quoting just under an amp of power draw at 5 volts and 12 volts. So let's see if the board can handle this. And ignore that it's kind of floating in midair here. I didn't realize that my cables were going to be this short, and I'm not trying to fully install it because I don't know if it'll work properly yet. Now, sadly, this is where my streak of luck with this project ended. These drives were definitely having issues spinning up, and when checking with a thermal camera, I could tell that only the bottom 2 managed to power up properly and continue spinning. After some probing, I found out that it was sadly still an issue of the voltage rails utterly collapsing, and in this case, it was mainly to do with the 5 volt rail, which had dropped to 4.4 volts by the time it was reaching the SATA cables. The output from the DC to DC converter was a flawless 5.000 volts though, indicating that the issue was really stemming from the MOSFETs that I had used, which ended up being IRF 9540s in the end, as opposed to the 9640s that I had been tinkering with on the breadboards. Yikes. Well, I tried my best to read the datasheet of these MOSFETs and make sure that they would be suitable for this application, because I knew that this risked being an issue, but maybe I messed that up. And it turns out that mess it up I did. And these MOSFETs are in fact very not suitable for this application, hence why the device isn't working. So after the caring guidance of AI, because I could not figure out what I was doing wrong, I came to the conclusion that the IRF 4905 would be a much better MOSFET for this application. This is because it has a much lower on resistance than the IRF 9540 that I've been using until now, and after ordering several of them and replacing all of the 9540 MOSFETs on the board, I was almost ready to give it another test. There was one other thing that I did though, and that was add a 47 kilo ohm resistor between Vout minus and the trim pin on the output of the DC to DC converter. I did this because these modules have the ability to trim their output voltage both up and down by 10%. I used the 47 kilo ohm resistor to trim the 5 volt output up to 5.3 volts, as this will give me a little bit of headroom for the voltage drops that will take place through the MOSFETs. and by the time the power hits the hard drives, it should be within the ATX spec, which allows for a maximum 5V rail voltage of 5.25 volts. With the new MOSFETs installed and 5 hard drives plugged in total, I powered everything up and all of the drives spun to life properly. Alright, this is a good look so far, but now let's give it a real hard test powering 8 7200 RPM SAS drives in the NAS. And I'm really pleased to say that while powering all 8 SAS drives and a 10 gigabit network card that was on an M.2 to PCI Express adapter, resulting in a total of 9 SATA power connections, this board ended up doing amazingly well. Everything was reliable, the voltage rails were at healthy levels, and really, everything was just doing well. Some of the MOSFETs did get quite hot, around 80 degrees Celsius, but that's well within their operational temperature range, and not too concerning a temperature to have inside of a computer either. This PCB is designed with the same mounting hole spacing as a 2.5-inch SSD for increased versatility in regard to mounting, and if you can mount it somewhere that has some airflow, it will be a lot happier. Plus, I also 3D printed a small sled for it that allows it to mount to a 3.5-inch bay, and that also includes a mount for a 50mm fan to blow on the PCB. The 50mm fan can be either a 5V or 12V fan, and can easily just piggyback off of the power available at any of the SATA power outputs. After trying this assembly out in the NAS, and ignore the fancy new drive bays in the top, that's a project that's coming out soon that's showing up because I filmed things in a weird order, I found out that the whole system felt a lot more professional, as all of the components on the PCB ran cooler even with a side panel on, and actually getting all of the drives connected to the PCB was a heck of a lot easier than before. But with that, I think that this project is done. I'm super happy with how this final product came out, and even though I needed to do a revision with the MOSFET choice I made, I think it all went really smoothly. I think that being able to convert a PCI Express power cable into a bunch of SATA power cables is really useful, as it can be hard to find power supplies that have enough SATA power on them for certain builds. Plus, most modern power supplies have their most current capacity and highest efficiencies on their 12V rail, and being able to make more use of that is never a bad thing. If you're interested in making one of these things for yourself, check out the link in the video description to an Instructable that has detailed written instructions on how to build one. Well, that's all that I have for you in this video. I hope that you were able to at least enjoy it, and maybe even learn a thing or two. In any case, I hope to see you next time. Goodbye.